Hello and welcome. It's me, Mr. Murphy, in my house. I'm glad, excited you guys will be able to see me through this whole time, and I think this will be pretty smooth transition to what we've been doing. As you notice here, we've got smartboard as we always do. Yeah, here we go. No warm up today. We might not even have a warm up for the rest of the year, which is exciting, and I don't have to go around grade papers, which is even better. This is already off to a wonderful start. So I was planning on telling you guys a story about what I did over spring break. Well, I didn't get to go down to the ranch this spring break, unfortunately, because of everything that's going on. So this is what I did last spring break. So this is me and a cow. They have like 50 head of cattle down there, which is pretty cool. Looks like smartboard file is not responding. So good news is that I'm building a computer, so we won't have any technical issues like this, like smartboard timing out. So it's still recording, but I don't have any access to anything. So building the computer tomorrow, which is going to be really fun. Anyway, I'll just continue telling a story about the cow just in case everything goes back. Yes, we're back. Okay, we're here. All right, so basically, I got to help deliver a baby calf, which is absolutely incredible, and proof of it is right here, which is kind of disgusting, but at the same time really cool. So mom, who's in the background over here, she actually stuck her head in between those two gates or fence panels or whatever, and she put herself in a head gate, which allowed us to safely help her out, because she's a heifer, so it was her first baby and she was having issues, complications and stuff like that. So anyway, it made it survived. You can see a photo of it just a week later that my uncle sent me. So it's now over a year old and healthy, and everything is going on. And what's cool is whenever babies are born, human babies, we slap the back of them to get them to cough out the amniotic fluid and to start breathing, and for their lungs to fill up with air for the first time, which is kind of cool. And with cattle, you tickle their nose. So we tickled the nose of the calf with a straw, and it sneezed, which was the most adorable thing ever, like a puppy sneezing, if you can imagine that. So yeah, it sneezed, and I got to be a part of all that, which is really cool. So City Boy got to play cowboy over last spring break. Unfortunately, I didn't get to do any traveling this time. But anyway, moving on. So we're going to talk about a circle. Circle is for this whole unit now is on circles. So a circle is a set of all points that are equidistant from the center point. So the word equidistant kind of tells us in the word here. Equidistant means that it's an equal distance. Oh, that's funny. Let's try that again. So it's an equal distance away from the center point. So this is called circle P, which is named after its center point here. And all the points that are the same distance away from that, let me change colors real quick. All those points that are same away from it, their distances here, that segment would be called the radius. And the collection of all these points together is going to give us what makes up the entire circle. So that's not new. You've seen that before. We're going to go through a lot of vocab today, basically. All right, radius is a segment with one endpoint on the center of the circle and the other one on the circle itself. So we have lots of different radiuses on this circle. Any point that's connected on the circle and the other point at the center point here would be considered a radius. So no big deal there. A chord is a segment with two endpoints on the circle. So this is not actually a diameter. The reason we know it's not a diameter is because it doesn't go through the center point, right? Now it would be a diameter, but any other segment with endpoints on the circle is considered a chord. And there are, of course, many different chords that we can make on a circle. It's probably a new word. You probably haven't heard of a chord before. All right, diameter, like we just said, segment two endpoints on the circle. That's a chord that goes through the center. So as soon as this goes through the center point here, that makes this a diameter, which cuts a circle into two semicircles, just like you probably already know from middle school. A secant line, you might not have heard this one before, but a secant line is a line that intersects a circle into two places. So here you got a line that's not a segment, so it doesn't end with endpoints on the circle. It keeps going through. So if we were actually writing this proper, we would put arrows on the ends of this so that we can make sure to distinguish that it's not a segment, but it's indeed a line. So it's going on forever. Anyway, so that's a secant line. Secant line intersects a circle in two places. We have a tangent line. So this one's kind of interesting. So a tangent line is like a secant, but it only intersects a circle in one point. So this blue line here right now would be considered a secant line because it intersects, of course, if it extended forever, which I'm not showing that right now. But that would be a secant line. And as we go across here, we would cross another secant line, another secant, because it's still intersecting in two places. And then we have another secant line, and eventually we're going to come to a point where it's now a tangent line. So this green or blue line here are tangent lines because it only intersects a circle in only one point. So there's actually, there's a postulate, I believe, that says that if a line intersects a circle, if it goes into the circle, and it's actually indeed on the inside, then it must also exit the circle as well. And that's one of the postulates. I forget which one it is, but it's one of the first ones that we have. Anyway, so the only difference there is that if we have a tangent line, it intersects a circle, yes, it only intersects a circle in one point because it never actually enters into the circle. So that is called a tangent line. And on Wednesday, I'm going to teach you probably one of my favorite days. It's going to be about NASA math is what I call it, but all about tangent lines. And it's going to be really, really cool. And I'm excited to show you that. So going to be some really cool graphics, and I think you're going to enjoy that one. It's going to go viral. It's going to be really cool. I already know it. All right, an arc is a section of a circle between two endpoints. So an arc is not the whole circle, it's just a section of the circle. So just like a segment is a part of a line, it's a segment of a line in a sense. The arc is part of the circle, but it's strictly the part of the circle, the collection of all equidistant points from the center point, that's a circle, that is in between A and B. So this is called arc AB. We annotate it with arc AB. Usually we don't have to put the word in front of it if you just see arc AB. This is a little bit redundant, but so that you can know what's going on. And that's referring to all those blue points there in the arc, which is the set of all possible equidistant points from the center point that is strictly in between A and B. I know it's a lot of math talk there, but an arc is pretty much exactly what you think it is. We have three different types of arc: major, minor, and a semicircle. So major arc is one that's larger than 180 degrees. A minor arc is less than 180 degrees, and a semicircle is half of a circle, which is 180 degrees. All right, so the first thing is arc AB. So when we're going from A to B, there's two different ways we can go. We can go the shortest distance between A and B, which would be this arc here, and that's indeed the arc that we're talking about. So that's arc AB. Don't be confused by going the long way around. We never do that unless we have a third point to dictate it. So this arc, which is going all the way around the circle, is not arc B. That would be called arc AEB or ADB or ACB. That's how we would specify the major arc. So anyway, this is a minor arc because it's less than 180 degrees, less than half a circle, and this is arc AB. Next one is arc ADC. See how this one now has 3 points defining it instead of just 2? That's a clue that this might be a major arc or a semicircle. It's not, but it also still could be a minor arc. So ADC, how do we figure that out? So we start at A. We want to go the shortest distance to D. So we're not going to go all the way around counterclockwise. We're going to go clockwise to D because that's the shortest distance. So from A, passing through D, and then the third point is C. So ADC. That's going to be this arc here. So I'll pull it over so you can see it. Now that arc is going to be a major arc because, as we can clearly see, it's larger than a semicircle. And if you see the diameter here, that would be a semicircle. And then we would extend it on to A. So this is, of course, a major arc. Next one we have is arc CE. So this one only has 2 points, which kind of tells us it might be a minor arc, or it's probably a minor arc. But if we look, CE is going to be, let me move these out of the way real quick. So CE is going to go from C to E. Now we're going to go the shortest distance from C to E. So we're going to go to the arc on the bottom, which would look like this one over here. Wrong one. Or the arc on the top there, or is it the arc on the bottom? So that's my question. Is arc CE talking about the arc on the bottom or the arc on the top? And how do we know? Well, it's actually ambiguous. It could be either one. So just like the donkey postulate, it's not well defined. And so we can't actually define the semicircle with only 2 points. We have to use another point. So what if we talked about arc CDE? CDE. So the shortest distance from C to D is going to be the one down here and then going to E. So that's obviously talking about this orange color or tan color, depending on what it looks like to you. All right. And it's color coded, so kind of a dead giveaway. So what if I wanted to define this green arc, the one on the top, not the one on the bottom. Well, on the bottom, we only have one other point in between those two, so it has to be semicircle arc CDE or EDC. But for this one, we got two other points we can pick. So we could call this arc CA, shortest distance between C and A, E, or you can call it CBE, or we could go from the other side as well, just like defining a line or a segment. It doesn't really matter the order. All right, so that's the major arcs are larger than 180, minor arcs are less than 180, and a semicircle is equal to half a circle, which is 180 degrees. All right, so major or a minor arc. If I'm talking about AC here, am I going the shortest distance from A to C? Well, that's going to be the minor arc. That would be the blue one. So if we're just saying AC, we're talking about the minor arc, the shortest distance between A and C, which is the blue one. Now, if I wanted to talk about the major arc, that would have to be using a third point here to tell us that we go the shortest distance from A to D, which is now going around to clockwise instead of counterclockwise to C. So ADC is going to be referring to the major arc, which is the one that's larger than 180. All right, same thing here. If I'm talking about arc AC, that's the shortest distance between those two, which is going to be the blue one here. If we want to talk about the major one, we have to use a third point. We could either use ABC or ADC. It really doesn't matter between those two. So this is going to be major arc ADC. So the shortest distance from A to D and then going from D to C. And that's talking about the green one there. All right, so the only other thing I believe that I have to tell you today is central angles. We'll do inscribed angles tomorrow. But central angles are angles in the center. So it's the word kind of defines what we're talking about here. So kind of working on my transitions, but anyway, central angle is an angle that's formed in the center of a circle. So where the vertex of the angle is going to be the center point. Okay, so 50 degrees here is a central angle for this circle. So the measurement of the arc, so we have BC here. This is arc BC. Remember, just like with measurements of segments, if we put a little m in front of it, that's what it's talking about. So this is the measurement of arc BC. So we want to know not how long it is, that's arc length, but what's the measurement? What percent of the circle? And it's not really percent, but how do we measure how big this arc is? Well, that's going to be measured by its central angle. So this is 50 degrees for the central angle. So we'd say that the measurement of arc BC is also going to be 50 degrees. So then what's the measurement of arc AB? Well, AB, the shortest distance from A to B, is this one over here. Well, we know this one is 50 degrees, so what's this blue central angle going to be here? And I can hear you screaming through through the internet of it's a linear pair, right? So those two are supplementary to each other. So what is the supplement of 50? Well, this is a great opportunity for me to show off one of my tricks that I've been hiding the whole time, this calculator over in the corner. All right, so we want to find out what's a supplement. So 180 degrees minus 50, which is going to leave us with 130 degrees. So thank you to Texas Instruments for providing that emulator, SmartView emulator, for us during this this pandemic, which is actually really, really cool. So get to play around with that, and I'll be using it next year too, which is fun. So that's 130 degrees. So what's the measurement of arc AB? That's 130. Then the only one we have left over would be ADC. So shortest distance from A to D and then to C. So that's obviously a semicircle, right? And this is a diameter because it's a chord that goes through the center. So that has to be 180 degrees. Then what do we know about the sum of all three of these angles? Well, they add up to 360 degrees, right? So we know that as well. Another way we could solve it. All right, so that's 180. Last one we have is BAC. So notice how this one has three, it's defined by 3 points. It means it's probably going to be either a semicircle or a major arc, but not always. So let's go the shortest distance from B to A. So B to A, we're going to go counterclockwise because that's a shorter distance than going all the way around here. That's the rule we follow. So always go the shortest distance. So B, A, and then C. So all the way back around. So in other words, if we notice, that's everything except for the measurement of arc BC. So there's two different ways we could solve for this. We could add the 130 and the 180 together, which really isn't that difficult, especially because we have our calculator. But we also could subtract 50 degrees from the 360. So I'm going to do it that way because that's how my brain likes to work. So 360 minus 50, which is going to give us 310 degrees. So the measurement of BAC is going to be 310. All right, so cool stuff there. I had a feeling that was going to happen. All right, next one. So properties of central angles, this is actually kind of cool. So we're talking about arc AB here. This actually should have a little m in front of it because we're talking about the measurement of the arc. That's why it's in 45 degrees. So if the measurement of the arc AB is 45 degrees, then what do we know about this central angle, angle AEB? Well, if you remember, the central angle is how we measure the arcs. So if the arc is 45 degrees, that means the central angle is also 45 degrees. Well, notice here, these are two diameters, right? So they are forming straight lines. So then what do we know about the angle down here? Well, that's a vertical angle, right? So that has to be 45 degrees as well. Okay, so if we have two diameters, then what do we know about arc DC? Well, DC also is measured by the central angle, which is 45 degrees vertical with that one. So notice kind of like this chain reaction that happened here. And we also could solve for the angle on the side here as well, right? So that would be the supplement of 45. So let me try my drawing tool here. Should I change colors? Yeah, we're going to try green. I like green. As you can tell, it's on my wall in the background. All right, so 45, so 180 minus 45 is going to be 135, right? So then what's the measurement of this arc over here? 135 degrees. All right, then the vertical angle on the other side, still 135 because it's vertical with a central angle, and this arc over here is 135 degrees. So when we have two diameters that both, of course, go through the center point, we know one of the angles anywhere on the circle, we can fill in everything else. It's just kind of a giant chain reaction that happens, which is kind of cool. All right, so we're going to go through our vocab again, just kind of quizzing ourselves, making sure we know this. And again, half of this vocab words you already know from middle school. So I know it's kind of weird. I'm talking to you guys and can't really, can't wait or anything. So just quiz yourself and see if you can get it. So what is a set of all points equidistant from a center point? What do we call that? So it looks like this. It's called scaffolding. All right, so from the center point, it's a set of all possible points that make up this figure, geometric figure. Well, it's called a circle. Ding, ding, ding. Did you get it right? All right, I'm totally talking to myself, and it's fine. All right, a segment with one endpoint on the center and the other on the circle. So it's a segment, so it's not a line, but it's a segment. It's got two endpoints. One of the endpoints is on the center of the circle, and the other one's on the circle itself. So what would that look like? What is that called? So it looks like this. So it's a segment. One endpoint's on the center of the circle, and the other one's on the circle itself. What do we call this segment? And of course, it can be anywhere on the circle, right? That's called, I know you know it. Okay, a radius. Nothing really new there. Certainly hope. Oh, maybe I have to click off of it. There we go. Now my keys will work. All right, a segment with endpoints on the circle. Oh, I don't like that color. Or that color. Or that color. Segment with endpoints on the circle. So now it's still a segment. It's got two endpoints. Both of them are on the circle. So it looks like this. What is that called? This is probably a new one you haven't heard of before. And we know it has a special name when it goes to the center point. You probably know what that is, right? That's a diameter. That's the next slide. My bad. But what is it called when it doesn't go through the center? So that's called a chord. Yes, a chord. All right, segment with endpoints on the circle and a midpoint in the center. So it goes through the center. So again, a special chord that goes through the center is called a diameter. And what's special about it is it cuts the circle into two semicircles, and it also, of course, measures 180 degrees on both sides. So that's 180 degrees and 180 on the other side as well. All right, a line that intersects a circle in two places. So what do we call a line that intersects a circle in two places? So this one you probably haven't heard of before, but it looks like this. Remember what that was called? Oh, no. I already showed you. Okay, so that one's called a secant line. And then what's special about a secant line as soon as it only intersects the circle in one point? So a secant line assumes that if it intersects a circle and goes inside the circle, then that means it also must intersect the circle again to exit the circle. It's basically constraining it to be coplanar, in other words. But what happens whenever that only intersects in one point? It never actually goes into the circle. Do you remember what that one was called? It's the next slide. That's why I'm transitioning like that. So that one that only intersects a circle in one point is called a tangent line. So it's like a game of duck, duck, goose. Secant, 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 secant. Tangent. All right, so this is our tangent line because it only intersects in one point. And again, Wednesday, come back because this is going to be pretty cool. What we can do with tangent lines that relates to NASA and like space math. So I think you guys are going to enjoy it. Wednesday. Tune in Wednesday. All right, a section of a circle between two endpoints. So it's a part of a circle. It's got two endpoints. So it kind of sounds like a segment, but it's a part of the circle. So it's not a straight segment. What do we call that? Again, don't like those colors. So here we have two radiuses, but we're talking about the section of the circle that's between the two endpoints. So that would be like this section of the circle. I'm doing my best. Okay, we're gonna say that's good. What is that called? That's called an arc. My handwriting is atrocious. All right, so that is an arc. At least I'm self-aware. That's the first step to recovery, is admitting that you have a problem. What kind of types of arcs do we have? Major, minor, and semicircles. So I would ask you, if we were in class together, which one of these, give me a name of a minor arc. Well, there's lots of them. AB could be a minor arc. Give me a semicircle, so that would be ACD. Again, we can't just define a semicircle with 2 points. I'm really struggling here. So we can't just say AD, because then we don't know if we're talking about AD, the semicircle on the top, or AD, the semicircle that goes on the bottom. So if we want to define it, we have to do a semicircle with 3 points, just like defining a plane. You got to have 3 points for that. And then, of course, a major arc is when we go beyond a semicircle. So that could be, I would change colors real quick. We'll do red. No, I like blue. All right, so the semicircle would be a D or a CD, and if we kept going around until we got back to E, that would be a major arc. So that would be ADE. So this is arc ADE. That's all right. So now we're done with the lecture. That was 22 minutes. I'm going to try to shorten those down as best I can, but you know, I'm working with a lot of new technology here. So sorry about that. That took a little bit longer. And today was mainly just a lot of vocab. It'll go quicker in the future. So here's the assignment. Just like normal, I would normally pass these out to you and have them printed off, but we don't have that. So if you need to pause the video, go to Google Classroom, find the assignment. You might want to print it off if you can. That's probably the best thing to do. But if you can't print it off, you can always just look off the assignment, write your answers down, or show your work on a separate sheet of paper, and then just cross off the answers as you go or something like that. Again, printing it off is probably the best bet. If you have an iPad or a tablet or computer, there's also, because it's a PDF, you can edit PDFs, and there's PDF editors out there that will let you annotate it, maybe even with just your mouse, not using kind of some of the cool technology I'm using, but anything like that. So I'm going to let you guys solve that problem. But keep in mind, you're not turning in these assignments and you're just grading them as you go with your answer bank. So it doesn't really matter how you decide to do it. So whatever floats your boat. So I'm going to go ahead and pretend like you guys all have this printed off and you're ready to go. And we're going to go. So describe the following arcs of circle B as minor, major, or semicircles. So GJ. And I know the assignment looks like it's long, 41 problems, but it's gonna fly by. These things are really simple. All right, so GJ, starting at G, the shortest distance to J is going to go counterclockwise, and that's going to be a minor arc. So you can cross it off on the answer bank. What about HI? So HI, the shortest distance between H and I, is a minor arc again. So you can cross off the other minor arc, which I don't have listed here. And then HIJ. So this one is defined with 3 points, which is cluing us into it's probably a semicircle or a major arc, but it might not be. So let's go from H, the shortest distance, to I, and then all the way around to J. And we notice that that's going to have 2 endpoints on the diameter. Well, if it's an arc with endpoints on the diameter, what kind of a arc is it? Well, that's going to be a semicircle, right? So here is our semicircle, arc HIJ. So HIJ, semicircle, which we know is going to be 180 degrees. All right, moving on. Find the measure of each arc and circle R. So UT. Now we actually want to find their measurements. So UT has a central angle of 114 degrees. So what's the measurement of the arc UT? I wish I had my smartboard. It's okay. Well, we're going to do the best we can, and my handwriting is going to improve. I bet you I still can't draw straight lines, though. Oh, dang. Look at that. That's an inside joke. If anyone's not in our class, they have no idea what we're talking about. I wonder if they think I'm gay already. Moving on. I'm straight. We've established this. It's like definitive proof. Just ask Anna. She'll tell you the truth. I won't use your last name because, you know, YouTube. But all right, so 114 is the central angle. So the measurement of the arc is also going to be 114 degrees. So that would be 114. You can cross that off of your answer bank. All right, ST. So ST is this arc here. Well, if we have a diameter, what is the supplement of 114? So we're going to do 180 minus 114. Why am I writing this out? I can just do it here. All right, so we have 180 minus 114, which will give us 66. Okay, cool. So this has to be 66 degrees, which means the measurement of the arc is also 66 degrees. Whew. Working on that handwriting, guys. All right, what about SV? So SV, the shoot. How do we figure that out? SV. Okay. Well, I notice over here, I got a right angle, and this is a diameter. So what does this one have to be? Right. The supplement of 90 is 90. Good. Wow, that took me a second. I was worried. I'm sure you guys got it though. Not the undo button. All right, find the measure of each arc in circle D. So more of the same stuff. Let's just look at our circle for a second. So we know arc GF, girlfriend, you know that thing I once had. That's 70. Yeah, the jokes, they just keep rolling, even though I'm talking to myself. It's all right. So we know the central angle is also 70 degrees. Another thing you notice is that IF is a diameter. So this is a semicircle. So the whole thing altogether is 180, right? And if this is 70 of it, what do we know about these two angles? Well, that's going to be the supplement of 70. It's sad that I'm actually putting this in the calculator, but whatever. So 180 minus 70 is equal to 110. And then what do we notice? So these two add up to 110, right? But what do we notice about these two measurements, or these two markings? Well, they tell us that those two arcs or those angles are congruent. Those are congruency marks, which means that their same value, we'll call it X, right? So then what does it have to be? Well, if those two X's have to add up to be equal to 110 degrees, then that means that one of those X's has to be equal to half that, which is 55 degrees. So both of these are going to be 55 degrees. Hey, the handwriting's coming along. All right, so now that we've done that, we've pretty much solved everything we need to know, and we're good to go till we get to the point that we have to do some other stuff. So angle, what's the measurement of angle EDI? So EDI is going to be this angle here. Uh-oh, we don't know what that angle is, right? So how are we going to figure out this angle? Let me give you a moment. Why didn't I mark this one over here? Well, because we have two diameters. Those are straight lines, right? The segments. So then what do we know about those two angles? They're vertical angles, right? So if this is 70 degrees, this angle over here also has to be 70 degrees. Okay, good. So don't forget all those basic things from the first semester. What is the measurement of arc EF? So EF is going to be this arc here. Well, if that's 70, the central angle has to be 110, right? And it's also the sum of these two, right? Those are vertical angles as well. Oops, the undo button. I could change colors there to kind of show you what's going on here, but this angle has to be the same as that angle. So if this is 110, that means this also has to be 110. So we got 110. What about GI? Well, if that's 110, this one is also 110, so good to go. That was pretty easy, no big deal. All right, 28. So this isn't super clear, so I'm going to do it with you, but they're going to say this angle here is the expression 2a minus 45. And the other angle here is the expression a, or just the variable a. So what do we know about those two angles together? Well, if this is a diameter, that means that this part over here has to be 180 degrees, right? Because it's a semicircle, and it's a straight line. So it's 180 degrees. So these two over here have to add up to 180 degrees. So if we add them together, altogether that's going to give us 3a minus 45 is equal to 180. So when we add 45 to both sides, Wow, the handwriting struggles. All right, so 3a is equal to, what was that going to be, 225? So when we divide, I'm just going to put that right in the calculator, even though I already know the answer. All right, so we're going to do 225 divided by 3, which will give us 75. So a has to be equal to 75. Pretty sure that's one of your answers. Yeah, that should be one of your answers. I don't have the answers in front of me, so I'm just assuming that's right. Hopefully it's not 15. I had a feeling it was 15, but that's probably a different problem. Anyway, I might have a typo. Oh, by the way, if I do have a typo, just comment on Google Classroom, and we'll just save everyone else some headaches. So we'll call out all the typos, and that will make sure that I know that you're paying attention too. So good for you. That's why I did that. Not because I'm human, but because I was trying to make sure you were paying attention. All right, 31. Ooh, what's that lovely shape there? Count the sides. 1, 2, 3, 4, 5. That's a pentagon. Well, we know the central angles all together, and it is a regular pentagon. We know that because all the sides are going to be the same, which means the angles are all the same as well. Okay, so we also know that the measurement of all the angles on the inside is 360. Well, if we're dividing it into 5 different sections, then what is the central angle going to be? So 360 divided by 5, which is going to give us, probably already know this one off the top of your head, right, because of our polygon unit, but it is 72 degrees. So the central angle is going to be 72 degrees. 31. Right, 32. We want to find the measurement of arc EYD. So EYD is going to be this angle here. So to find the measurement of this arc, that's going to be the same as the central angle, which is marked by this question mark here. So just like the other problem, we got to break it down. So this is 40 degrees. That means this part here is 40 degrees. Oh, wait. Those are totally ends of diameter, so those are vertical angles. So this one has to be 40 degrees. But let me go ahead and solve the next part so you'll know how to do it. But these markings here tell us that those are congruency marks. So these two marks are, these angles are congruent. So if that's 40, what's left over? So if we do 180 minus 40, it's going to be 140. So both of these together are going to add up to 140, just like we did in the last one. So divide it by 2. That's going to tell us that both of these are 70 degrees. And by the way, if those two add up to 140, then the vertical angle on the other side is also going to be 140 degrees. So you're welcome. Oh, these are fun. So the last ones, what is the measure of the minor arc formed by the hands of the analog clock? So if it's 2 o'clock, do you guys even know how to like read clocks? Anyway, you know, non-digital ones, analog clocks. So we have the minute hand and we have the hour hand. So we'll start with the minute hand. If it's 12 o'clock, that means that our minute hand, you know what, I can do better than that. Check it out. I got a new toy I'm going to show off. Yeah, look guys, I learned how to draw straight lines. Boom. Isn't that gorgeous? All right, so the minute hand's a long one. That's going to be going to 12 because it's 2 o'clock exactly. There's no minutes, right? Or 60 minutes, however you want to look at it, modulo 60. All right, so then 2 is going to be where the hour hand is going. So from the center, the shorter hand is going to 2. So the question we have is what is the measurement of the arc that's created by those two hands? So what is this central angle here? All right, so to do this, we have to look at the whole circle. The whole circle is going to be 360 degrees. It's also broken up into 12 pieces because there's 12 hours for the clock. So what we're going to do is going to do 360. We're going to divide that by 12, which is going to tell us how many degrees we go over for each hour. So for each hour, so from noon to 1 o'clock, that's going to be 30 degrees. And then from 1 to 2 o'clock, it's going to be another 30 degrees. So all together at 2 o'clock, the hands are going to have make a central angle of 60 degrees. So what a cool problem. I like that one. So what if it's 2:30? So 2:30, the minute hand, or sorry, the minute hand is going to be going to 6, right? Because it's 2:30. So let me see if I can. I was pushing the wrong button. Okay, there we go. Because I can't draw straight lines and I'm self-conscious about it. All right, so that's going to go straight down to 6. And then 2 o'clock. Now this is not going to go straight to 2. It's actually going to go halfway between 2 and 3. And the reason for that is because the minute hand is at half, and so it's halfway between 2 and 3, because the min hand is at 30 minutes at the 6, right? So what is this angle? Well, we know that we've got 30 degrees for this one here. We got 30 degrees between those two, and another 30 degrees here. And then we have halfway between 2 and 3, which is going to be 15 degrees. So add them all together. It's 90 plus 15 is going to be 105 degrees altogether. So the central angle at 2:30 formed by the minute and the hour hand is going to be 105 degrees. There we go. And I think that might be it. Yeah, that's it. So 35 minutes, 36 minutes. So went a little long. We'll try to make them shorter in the future, but you've got your homework. You've got your answer banks, so grade them as you go. And it was this is good. I think it's just like what we've been doing in class, just now virtual. And if I talk too fast for you, you can go back and you can look at things again with our definitions. I'll work on getting notes out to you guys, but all my notes are stuck at the school and I'm not allowed to go there, so it's just an added problem. So I hope you guys are doing well, and I hope this went well. Welcome to my house. I literally painted that wall like 2 hours ago. Yeah, because I'm remodeling a lot in my house. So I love green, and I'm really excited about that wall and my bathroom. But you guys already saw my bathroom. Why did you see my bathroom? I don't know. That's because I'm weird and I need help, but that's okay. We're all in this together. So see you guys. I'm actually going. Bye.